Okay, so it's the last day of the last activity of our program. So thanks everybody for staying to the end. And today we are excited to have Bin Dong, who is speaking from Peking and is set up a very large center focused on AI for mathematics, which will tell us about their activities. So Beijing International, well, the Center for Machine Learning Research, Peking University. And so, yes, I look forward to hearing this. Ben, please.
All right. Yeah, thank you, Mike. And thanks for the invitation. And it's quite unfortunate that cannot show up in person, so I had to do this online. Just a little bit a short introduction of myself. And I'm from Beijing International Center for Mathematical Research at Peking University. I'm also affiliated with the Center for Machine Learning Research. So I label myself as an applied mathematician, but I work fully on machine learning and AI, especially the interface between machine learning and mathematics for the past a few years. And so today I'm gonna introduce it's got AI for mathematics, and it's an emerging and very exciting field, and it's the main theme of this long program. But I will spend some time to present some of our effort at Peking University, and also what we have been working on, and how we actually envision the future interplay between AI and mathematics. And the subtitle title of my talk is called "From Digitalization to Intelligentization." I'll just show how we see how we can move from through this process. So the content of my talk is very simple. I'll give you some little background, and then the progress. From my perspective, the important progress that at least those progress that enlightened us, and then what's our current plans, and what we have already done, and what we're actually planning on doing next. Okay, so first I'll briefly review the history of AI, and especially entanglement between AI and mathematics. So we all know that the term AI comes from the Dartmouth conference in 1956, and if you look at the main founding fathers of AI, of that meeting, 6 of them are either having a PhD in mathematics, or they're mathematicians themselves. And the development of AI has some ups and downs, and as we all know, but the renaissance of AI begins around 1990, and then gradually become a rapid growth or an uprise in 2012, mainly because of deep learning. And in the very interesting book written by 2 computer scientists, Russell and Novick, they describe the reason of this renaissance around 1990 is because of the victory of the NEET camp. What is the NEET camp? It's those who believe that AI should be based on mathematical rigor, over the Scruffy camp, those who prefer to try diverse algorithms, methods, extensive hand coding, and incremental testing. And of course, both approaches are important, but the shift towards the neatness suggests that the field has reached a certain stability and maturity. So this is what described in their book. But at the rise of deep learning, which is around 2012, actually I started working on machine learning around 2016 because I've seen the amazing results produced by deep neural networks, and I was curious, why these seemingly less mathematical and hard to interpret models that can beat the traditional mathematical models so badly. So I want to understand why it works so well, but I still couldn't understand why it still works so well. It's still, I think, mainly a mystery, and also the more recent rise of foundation models. But what I can see is that the NEET camp faces challenges as the scruffy gains momentum. When I was a PhD at UCLA, I got my PhD from UCLA. I worked on image processing, but at that time, the algorithms or the models mostly variational PD models and wavelets worked very well, and also later compressed sensing, and during that period, I think theory is actually ahead of engineering approach. In other words, NEAT is ahead of the scruffy camp. And computer scientists and engineers, they also do a lot of theory. They also rely on theory. They read theory papers, they write theory papers to guide them to design better and more effective algorithms. But that has changed with deep learning. And what from my own perspective is that I can see the gap between theory and applications has widened, and it's become larger and larger. Okay, and the scruffy approach has been quite effective, although it has some downside of it as well. So even though the current AI has been very much more powerful than the previous generations, but there are some very major drawbacks of AIGC. For example, we know that GPT-4 is still weak at reasoning. At least, what GPT-4, AI like GPT-4 is good at and bad at is very different from human. Sometimes it makes ridiculous mistakes, but sometimes it gives amazing, results. And also, a video generation models such as Sora, we have seen plenty of examples where it violates, physics. So these AI models, they don't really understand, what is rigorous reasoning in mathematics and what is really the physics. So it's not, embedded, hard-coded in their, modeling. And the AI research, I think, needs theoretical guidance because to do ablation studies, with a model that has, tens of billions or hundreds of billions parameters is just not, it's just too expensive. You're going to have a unbearable electricity bill if you want to do ablation studies. So I think the search for better architects, the search, the finding effective algorithms to generate high quality data, to polish the data and to process this data, and also the training algorithms, it's all of that. I think it's under explored because of if you purely rely on engineering, just try and error, it's just too expensive. And also these AI models, need interpretability. We don't quite understand how these artificial brain, if you may, thinks, and when it makes mistakes, what has been going through in its artificial neurons. So we don't quite understand that, and also we are facing safety issues. So all of these, I think, calls for theoretical guidance. But the development of AI is so rapid that theory find a very difficult time to catch up. We have been studying MLPs, 2-layer, 3-layer, and then just a multiple layer MLPs and shallow transformers. But we're moving slowly, but it's still very far. It's very, very far away from the actual architects that engineers actually use in practice. But on the other hand, AI research needs theoretical guidance. So it seems like we're facing a dilemma. So AI is moving too fast for theory to catch up. At least this is from what I see. But they also need theoretical guidance. So what can we do? What can we as the theorists do? There was a very interesting fireside conversations led by some leading statisticians earlier this year. I think it's in March 17. I watched almost all the videos. It's very inspiring. And David Donahoe, who's a leading statistician, was also a applied mathematician. He made this comment during his talk. He said, "Let's wait it out," because he believed that soon the scaling law will hit its limit. But of course, this is maybe debatable, right? For me, I don't think that scaling law is going to hit the limit very soon. And also, the scaling law depends on the architect, on the quality of the data that you use, and also on the way that you actually train, right? If you use, for example, you use just when you deploy it and use sort of reinforcement learning to actually deploy it, and you generate a lot of data, and then you improve your model using data. And that's a very different way of training, based on supervised learning. So the scaling law depends on all that. So I would not rely on the slowing down of the progress of AI. Wait for them to actually come back and ask theorists for help. I think maybe we can just do this more proactively. We can actually improve, we can grow along with the development of AI. And so let me explain this chart a little bit. So we all know that from right to left is math for AI. And most people would think that, okay, so math for AI maybe use mathematical rigor to propose more effective AI algorithms or to design new and more effective AI models. That's definitely one big part of math for AI. But another part of math for AI is that mathematics can provide the training of AI with high quality data, and also the way we can actually use the way learn from the way we train mathematicians to actually train larger language models, so that the large language model, the reasoning ability of large language model may better align with with human mathematicians. And then on the other hand, we can also use AI to help us to improve mathematical research and education. Okay, so that we can actually complete this this circle, and math can help AI, and AI can help math, can help with math, and maybe this two fields will actually grow together. So but before we can actually move on, we need more evidence to make this argument more credible. Maybe for some of you, you don't quite understand why this is actually a viable approach. So the first question maybe we should ask ourselves is that what can AI do for mathematics? And are there any aspect of mathematics that need assistance, with powerful algorithms like AI? If you look at the success of AI in other fields, in natural science, and I think the key for their success is that the improve of efficiency. AI can quickly generate a set of plausible solutions for the problem that you have in hand. And that set of plausible solutions, maybe most of them are actually wrong, but at least it can quickly narrow down the search space tremendously for many cases. And I think that's pretty much the main reason why AI has been successful in many other fields. I think for mathematics, it's the same thing. So let me explain a little bit, what do I mean by efficiency in mathematical research? So first of all, mathematicians spend tons of time to prove, not only generating proof, but to verifying proofs. For example, this is actually in the discussion earlier last year, on whether large language model can actually help mathematicians to expedite paper reviewing. We spend a lot of time checking with the proofs, and then the proofs using natural language. There's no guarantee that the proof in natural language is 100% correct, and people make mistakes all the time, and sometimes the mistakes hidden in the proofs, maybe realized decades after the proof has been published. So this is one aspect that maybe AI can help us to improve in terms of the efficiency. That is to generate and verify proofs. And another aspect is that we often say, well, at least I often say this to my students, that we're standing on the shoulders of giants, right? We're doing research based on our academic ancestors. But do we exactly know the location of that shoulder? It's quite often that one of my students will come into my office and show me some very exciting ideas, and he or she just had. And after a discussion, the student will ask me, "Do you think this is new? Has anyone thought of something like this in the past?" I wouldn't know. I would just say, "Okay, so let's search on Google." But it's very often that the thing that you have thought of has already been thought of in the literature, but it's just the current searching engine like Google or Google Scholar would not actually give you a very precise match, because to give a high quality match, the search engine need to understand mathematics. So this is in machine learning term, it's called semantic search. So finding relevant results, if AI can help us quickly find whether a theorem that we have thought of is really new, and so that we can focus our time and effort on on really innovative stuff, is rather than just recreating something that people have already thought in the past. Okay, this would also be a huge efficiency booster. And also, it's also quite often in our daily research practice is that we have a new problem that we have a problem we want to solve, and we need to constantly learn new existing tools, and we want to use them. So to do that, we need to learn them, and to master a new set of theory or complicated tools, it takes time. And sometimes it happened to myself when I first learned deep learning, and I want to use theories from optimal control to probably understand it. But I wasn't very familiar with the theory of optimal control, so I spent quite a few months to study it. And then I start to realize that the theory of optimal control is too ideal to fit the flexible architects of deep convolutional neural networks. So just imagine if I can actually reduce that amount of time to just 1 week or two, to realize that maybe the tools that you thought that might be useful is not actually helpful. Or maybe I was wrong with that. Maybe at the aid of AI, I can actually not only quickly understand the tools, but can actually inspire me what's the proper use of this tool to attack my problems. So these are some examples that I think are quite important, and it can be solved, and you can significantly improve efficiency in doing mathematical research. And there must be many other examples that you guys may think of. So I think currently mathematics is not taking enough advantage of technological advancement. But to use a certain technology advancement to help us to do mathematical research, it has to be AI, right? Because we're doing mathematical research using our brain, and to aid with our thinking, we need to have a thinking machine or thinking model. But the AI in the past is not that very helpful. We don't want to use the AI model in the past, but now I think it's getting to a stage where we can start to work with AI to improve it, and use the improved version of AI to help us to improve efficiency and do mathematical research, and to get this circle going on. Okay, so the main thing of AI for mathematics is actually to develop AI model to assist in mathematical research and also in education as well. For example, search and retrieval, auto-formalism, theorem proving, counterexample generation, and so I'm sure that you guys have seen many examples in this long program. So I won't bore you with the details. So now let me quickly review some of the examples, and I'll categorize them into two categories. The one is mostly using AI to inspire mathematical research, but human mathematicians doing most of the work. And the second one is it's more it's more aligned with large language models, with automated or AI theorem proving, based on the proof assistant such as Lean. Okay, so maybe the at least in my opinion, the most recent signature work in AI for mathematics is this work done by DeepMind and Jordi Williamson. So without this blue circle, if you look at just the black boxes, this is traditional way of we do mathematical research. Let me, yeah, okay, to do mathematical research, and the blue one is actually is actually the ingredient from machine learning. So we may have in mind that maybe the two set of variables x and y, that has some some relationship. We want to write down the precise and neat and inspiring a formula f that describe the relation between F and Y. But sometimes it's the relation is so convoluted, and it may takes a lot of time to to craft a plausible conjecture and then eventually turn it into a theorem. So what machine learning can expedite this process is by generating a lot of examples of X and Y's data pairs, and through supervised learning, you learn a surrogate model to this F, and with this F hat, you can do all kinds of interrogation with this model and trying to acquire inspirations from this surrogate model F hat, and so that hopefully we can it can expedite the conjecture making, and just to reduce the amount of it's trial and error, and so that we can actually improve the efficiency of mathematical research. So this is actually the main idea behind the work done by jointly by DeepMind and Jordan Williamson, and they did just create some new theorems using this this diagram. So when me and my colleagues at Peking University, we read about this paper and we thought, okay, this is an interesting approach. Although in applied mathematics, we do this quite often. Actually, in my master thesis, when I was a master student at National University of Singapore, I do a lot of proving all kinds of inequalities. I actually use computational tools to help me verify whether I'm actually heading towards a plausible direction. But this is actually a first time that a machine learning model has been used in high-end pure math research. So I decided to work with my colleague Xuhua He. He's a professor at Hong Kong University. He's an expert in arithmetic geometry, and he had been working on finding the dimension formula for a fine deterministic variety. Well, I'm no expert on that, so I don't quite understand what that is, even though we had a joint paper and read the part that he wrote about ADLV, but I couldn't understand it, so I only understand the machine learning part. So we have worked on this project for 1.5 years before we had a paper, but in the first few months, we quickly rediscovered the virtual dimension formula that they have found in their previous work, and we also in our paper we also show how we counterfactually how we can gradually discover this virtual dimension formula by starting with very limited knowledge on the dimension formula of ADLV, and also through our computations, we realized that of course the virtual dimension is actually comparing to the actual dimension, it's actually an upper bound, and through our computations we also realized that there's a clear evidence, numerical evidence, empirical evidence that there is also a lower bound, and with that hint, Xuhua and his students and postdoc, they actually write down a new theorem, and they actually prove it, prove this theorem as well, and we also found a lot of observations, but for the moment we couldn't make a conjecture, a plausible conjecture out of it. So we reported all of these findings in our paper. So if you're interested, you can read our paper, and if you have any questions, you can feel free to contact me. And Xuhua, it's a mathematical question, you should directly contact Xuhua, and if it's a machine learning problem, you can actually ask me. Okay. So
Can I ask just a question?
Sure.
What type of machine learning did you use? Did you use supervised learning? Was there a data set? Did you use something else?
We can generate data set for the groups with with lower order, and it's the computation is based on induction. They have this formula based on induction, but the complexity is very high. So yeah, we use supervised learning, and the machine learning model is just MLP. It's a fully connected neural networks with hidden layers no more than 3, if I remember correctly. We also use SVM, this statistical learning models. but we didn't use very fancy machine learning models like graph neural networks or transformers. No, not yet. Just a
Okay,
simple.
so you made a database of these objects and with many attributes. And so you sort of followed the same procedure as Davy did out with the knots. You look at relations between.
Yes. Yes.
Okay, thanks.
Yeah. Yeah, we just want to see whether this approach apply to to other type of problems, and also we want to see what it's mainly for us. It's just our curiosity, just we by through this work we practice this this process with our own problems, and after that we just realized that this approach, although it's interesting and also it doesn't require a lot of computes, it's more computation power friendly in a certain way, but it's also limited because you need to spend some time to find an appropriate problem that can be solved in this way. And
Can I also ask, did you make your data set public?
Yes. Our data set, the program that used to generate the data set, and the training model, everything everything,
thanks.
everything public. Yeah. You guys can feel free to pick it up. Yeah.
Right.
Okay. So we found the limitations of that, and then we start to think, well, maybe there is a more systematic way of doing that. So I think the more systematic way is through training a large language model. So this is just a typical diagram that I copied online, so there's nothing special about it. This is just a general framework of that. But for mathematics, the most challenge, well, as a matter of fact, the whole at least from what I see, that the whole AI community has shifted to data-centric AI or data-centric machine learning for the recent several years. It's been like that. So to train a large language model that can do well in mathematical reasoning, we need very high quality data, and but the data is severely lacking. At least the public available data is severely lacking. Maybe DeepMind or OpenAI or some big high-tech company in China, they have high quality mathematical data, but certainly these data are not made public. So in the research community, people have been working extensively on how to create high quality data. And in my opinion, I do not think natural language math data, even though you may spend a lot of time and money to hire PhD student to label that, I think you need to augment that at least with formal mathematics, and so that you can really improve the reasoning ability of a large language model. Actually, we realized about a year from now. I wrote an article, but it's in Chinese, posted on the blog of our center, describing how we should rely more on the formal mathematics, and that's where actually we started this AI for Math program. Okay, so earlier this year there was this AIMO led by Tim and Terrence and a few other mathematicians as well. We teamed up with MIT and a lot of companies. Actually, Numina is actually leading. Jia Li, who's the founder of Numina, he's actually leading, gluing all of us together with Hugging Face, Mitchell, and Answer AI. Me and the two of my students actually help with finding and the cleaning and also the deployment of the AI models. Actually, we got the first place of AI model. This is it's the first. It's not the only. I think AI model they have separated into different phases, and we have won the first place for the very first set of problems. And we were actually happy for just 3 or 4 days until we see the news from DeepMind of AlphaProof. For me, I think I'm both happy and also a little bit anxious, because at least from the blog, I know there are DeepMind people here. I don't know when you guys will release the full technical report, but at least for the blog that I see, we have very similar, technical approach. So we had to, after we have seen that, we have a lot of internal discussions, and we decided to actually change our strategy a little bit because we do not have enough computes to compete with big high-tech companies. Okay, but anyway, just overall, if you look at the leaderboard of of AI, this is just in July of this year. I think comparing with other reasoning tasks like coding, mathematics is still lacking. Okay, we had an internal test of O1 using the math major undergrad problems. We have a set of 100 undergrad problems that covers 11 different lower division math major courses. I think O1 has reached the level of 75 out of 100. That's the average score of Peking University math major students. And it got about 35% of PhD course exams of Peking math, in our department. It's not passing PhD course. It's still far away. I think 50% will be the passing threshold for PhD course. So there's still a big way to go if we want AI to really assist in math research, or maybe even assist us improving some major conjectures in mathematics. So I think to reach that, we really need to rely on high quality data. So what do I mean by high quality data? I think the high quality data is the formal mathematics, not the informal math or the natural language mathematics. The formal mathematics using proof of systems such as Lean. And I think the digitalization means to converting informal mathematics, that is mathematics in natural language, to formal mathematics. So Lean is the formal mathematics that we have been mostly relying on, and this is just an example of proving that the composition of two continuous functions is still continuous using topological language, and it looks just like a computer language. And it can be verified, using using Lean, and this is the info field, and you can verify the proof 100%. If it's correct, it's 100% correct. If it's wrong, there's 100% there's a mistake in it. And I think I don't need to spend too much time on this. It's has attracted and it has entered the big league of mathematics. Not just a toy. It's just a teaching tool. I think it's started to attract more and more attention from the pure math community, and the math lab has been growing rapidly. But in my opinion, I think it's not growing fast enough. But it's just it's growing constantly, and I think we in order to expedite the growth of formal math database, we need to rely on automated, not just human labeling, but also rely on automated formalism models. So the reason that we've been teaching, earlier last year, we asked Johan Kamlin, and from Kevin Buzzard's school, he was Kevin Buzzard's postdocs, to give us 5 online lectures on Lean, and that's how we actually get started. Before that, there was very little people in China know about use Lean, at least not in the math community. So we started to train our students with Lean, thanks to Johan Kamlin, and then once we have some students who getting better with Lean, and we actually rely on these students to train more students. So now we periodically have Lean workshops and summer schools and winter schools, and we train about in average about 200 students per year, and we're producing more and more students who understand the language of Lean. And but for now, there's only a very small percentage of them will continue working with Lean. But I think that's at least quite helpful for us to advance AI for Math project in China, and also contribute to the Lean community, worldwide. But our experience with teaching students Lean is that it has a very steep learning curve. Just like what Terry Tao said in his blog, that it takes quite some time to learn about Lean, and also to master them, takes even more time. And also when you learn about Lean, doing formal math, can be a lot slower. In his blog, he said 25 times slower. And for our students, it could be 100 times slower to do formal mathematics comparing to informal mathematics. So this is actually our motivation. We want to have high quality data, and that is formal math. But to expedite this, we need to develop AI model. We need to train models to help mathematicians to create a high quality formal database, to enlarge MATLAB, and all kinds of formal math data. So now let me just introduce our work at Peking University. I call it PKU AI for Math team, and what's our current progress, and what we want to do next. So first of all, it's a very interdisciplinary, at least in mathematics, interdisciplinary, because pure mathematics, applied mathematics, and engineering, we all work very closely together. And actually, the leading driven force in our team are undergrad students. They're very fast learners, and they don't worry about writing papers, because writing papers is not their KPI. They just want to do some fancy and cool stuffs. So they're actually the leading force, actually one of the major leading force in this project. And also we have very talented PhD students, and we have a lot of faculty members in computational mathematics and also in pure mathematics. We have been developing all kinds of AI tools during this process to assist with creating high quality mathematical data set. So I can summarize these tools as two foundation models that we're building. The one is for reasoning, the other one is for computations. And our long-term goal is to create a co-pilot that can help mathematicians to interact with Lean, or not just with Lean. Maybe it can interact with the mathematicians to assist in their daily research or teaching efforts. Okay, so now I'm going to show you a series of videos and show you how what kinds of models we're trying to build for reasoning and computations. Right now we're still trying to train our own AITP models, but we're still gradually gathering high quality formal math data. So along the way, we've created some intermediary models to assist in helping to assisting mathematicians to do formal math. So the one is what we call Lean Search. We have already deployed that on on Zulip, and someone has already integrated with MATLAB. You can actually use that when you do formal math. And the other one is our recent work. We call it Herald, which is the auto-formalism model, and it does pretty good job in auto-formalizing statements. But to formalize proofs, it still needs some work, because the reasoning ability of large language models is still quite weak. So I'm going to show you the first video, which is the Lean Search, which is to help help a mathematician to quickly find the object, find the stuffs in MATLAB, which is a large database.
We are introducing ReasLab Smart Search, an AI-powered tool to find theorems in MATLAB 4. Let's start with the informal search mode. Imagine you're looking for Bezout's theorem. With ReasLab Smart Search, simply type your query in natural language and instantly access a curated list of relevant theorems from the informalized MATLAB 4 corpus. But what if your query doesn't yield the expected results? Take, for instance, searching for Wedderburn's Little theorem. A direct search might fall short due to the varied ways theorems are formulated in the database. This is where our query augmentation feature comes into play. With a single click, our GPT-4-powered augmentation transforms your initial query into one that's more aligned with the language of our corpus. For instance, it might expand Wedderburn's little theorem into a more detailed statement, such as every finite division ring is commutative, enabling our search engine to identify the corresponding theorem in MATLAB 4. A finite integral domain is a field. Empirical evidence from our benchmark testing shows that the query augmentation feature boosts the recall of our system by an impressive 8%. Moving beyond the informal search, we offer an equally powerful formal search mode. This mode is designed for those who prefer the precision of formal math. For example, when exploring theorems related to matrixed debt, our tool efficiently displays a wide range of relevant theorems, covering topics such as the determinant of a 2x2 matrix, the determinant of a family of vectors with respect to some basis, and the determinant of a block matrix. This feature is particularly useful for experts in formal math, allowing for a more targeted search experience.
Okay, so you can try this on Lean Search. We have already put that in our cloud service, and also Dr. Gadgil, he actually integrated. He spent a lot of effort. We really appreciate the work that he did. He actually integrated as a standalone repository into MATLAB. So just in MATLAB, you can just type hash Lean Search within a code block. You can actually use this Lean Search just easily. And we have a lot of just comments and very constructive suggestions, but we also have a lot of positive feedbacks. So you can we encourage you to try it. It's totally free. You can try it online and give us some more feedback so that we can actually improve this model even further. Okay, so this is Lean Search, which is for semantic search in MATLAB 4. Right now we're also working on extending this semantic search not just for MATLAB 4, but for for the mathematics field, so that so that the model can help us to find the really relevant, the mathematically relevant theorems based on the search input that you that you use. Okay, so that's one. The other work is actually what we call Herald, which is an autoformalism dataset and model. So it's both a dataset and a model. We also release that online. It's an open source a project as well. And we first we spend a lot of time. Also, we also spend some time to informalize MATLAB. First rely on AI models, and then our students comes in and clean it up. So we've created a very high quality NL and FL data set, a natural language and formal language data set. And then we build a pipeline, to do data augmentation to extend that, to close, it's close to 1 million formal and informal statement pairs. Okay, and we use that to train an auto-formalism model, and it's just auto-formalize a statement, and then we combine them together with Lean Proof, with DeepSeek Prover, and you can use other like Qwen 2.5 Prover. It's also quite good mathematics reasoning large language models, and we actually put them together. We build an agent, and so that we can just do auto-formalism, not just for the statement but also for the proofs as well. So this is actually the pipeline. If you're interested, you can read our paper. So this is the the situation of the data set that we created. We originally have about 300,000 method for original statement, and then we did a little bit augmentation. In our paper, we show you how we actually augmented using some mathematical invariant changes, and so that we can create it more but also mathematically meaningful statement. And then we trained an auto-formalism model, Herald, based on this, and comparing to the previous benchmarks. It has a significant proofs. It's not surprising because we have spent a lot of time to polish, to improve this data set. So this also shows that how important the quality of data set is in terms of the final performance of the trained model. We also combined with the DeepSeek Prover version 1.5 and tried it on the benchmark. So what we did is we do the natural language to formal language translation. So the input is the natural language statement and proof, and the output is the formal language statement and proofs, and with 128 passes. And this is the percentile of the, this is not the SOTA. I'm just showing that. Well, it's just put them together. It's not exactly fair to compare with the current SOTA. But we just show them as a reference results. And what our team is currently doing, our data division in our AI for Math project, they are actually doing they're also formalizing the stack projects. So we actually tried these tools on the stack projects, the section on normal extensions, and it translates the statement almost perfectly. There are some mistranslated, but you can just spend very few time to just correct them. And for the proofs, most of the proofs are not quite good, but two of the exercises in the stack project, it's it does auto formal proving correctly. So at least the translation of the statements is workable, at least for for my colleagues and our students working on formalizing mathematics. They say it's already a tremendous help, because we can quickly formalize a lot of elementary theorems and just put sorry behind that, and so that we can we know these theorems are correct. There is no absolute need or no immediate need to actually formalize them, but they need to use these theorems to to formalize some more advanced results. So this already a tremendous help. But later when we or maybe someone else have open source more power, have open source or more powerful automated proving, we're happy to combine them with Herald, and maybe we can just achieve one of our ultimate goal is that give me a paper or a proof written in natural language, we just automatically translate it into formal language and verify it, and so that we can really expedite paper reviewing. But I think the current bottleneck is the reasoning ability of larger language models is still very weak. Okay, so this is for the foundation models for the reasoning. We're also trying to build foundation models for computation as well. So so this model, we call this model PD former. So the computation model we're building is for solving PDEs. So we're trying to build a model that can solve all PDEs within a very big class. For example, all PDEs from continuum mechanics. That would include Maxwell equations and Navier-Stokes equations and shallow water elasticity, PDEs like that. So we actually build a new architecture, the reason that we build this new architecture is because we wanted to support more general, easily to generalize to different forms of PDE. So we use this graph type of construction to encode, to do a symbolic and numeric encoding of PDEs, so that it allows generalization of different forms of PDEs. And also the output is an implicit neural representation that is mesh-free, because we believe that God doesn't do mesh. We do mesh because we cannot really handle continuum stuffs. But mesh-free representation has its its advantage, and also this architecture enables fast adaptation and continual learning. So so we have released an open source, both the training data and also the trained model, which is a 3 million training data, even though it's in 1D, but it's a huge data set. Before us, people also do machine learning models for solving PDEs, but mostly the data set, the size of data set is like ranging from 10,000 maybe to 100,000. But we released the 3 million high quality data set, and also the model. We have a short paper and also the long paper. And
Can I ask you a question?
Sorry?
I just wanted to ask you a question. You're talking about verifiable, so rigorous numerical solution of PDEs. Is that what this does with error bounds and so on?
Yeah, it's not the rigorous numerical solution. So a foundation model for solving PDEs is that we trade accuracy with efficiency and flexibility, and well, it's I'm not saying that the model is not accurate. It's just the relative error of the inference solution is in the range of 10 to the -2, which is quite okay for many applications in practice. For example, inverse problems, design optimization, and for some predictive control. Because for some practical applications, the sensory data, the measurement has a noise that is beyond 10 to -2. So if you talk with people from from manufacturing, from engineering, they require that the accuracy is 10 to -2. That's enough, but they want the model to be very efficient. That means you input the form of the PD, they want to see results in millisecond, because to do design optimization or to do control, they need to solve PDs thousands or even tens of thousand times. So they want it to be very
This is a
efficient.
separate topic from formalizing mathematics.
Oh, that is not. No, this is not formal mathematics. It's for computations. So I just want to briefly show, computational math is a part of mathematics. So I include that as well. So this is mostly for computations. Yeah. Okay. So let me go through this very quickly, because this is not the main theme. I'm just showing that we could also build foundation models for computations, not just for reasoning. Okay. And in 1D, we observed scaling law. That means we can just that means the architects and also the way we generate data, it's plausible, so that we continue to move on to 2D. And in a couple of weeks, we're going to release our model in 2D as well. We have an even larger data set in 2D, and it's very interesting to see that the model is trained using supervised learning. That means we used traditional numerical solvers to generate data, but for some cases, the traditional solvers will fail. So we will just throw away those data where the traditional solver fails. But when we trained the foundation models, the PD formers, we tested the model on the cases where the traditional model fails, but the foundation model succeed where the traditional model fails. So you can see the foundation model as a certain interpolation of of the data, of the models that we had, and it can actually surpass the classical solvers for some of the cases. So I think this is a very interesting phenomenon that we observed. So this is the overall overview of the data that we tried different kinds of PDs from continuum mechanics, and these are all the relative errors, and these are the number of training samples, and the size of data set is around 25, getting closer to 30 terabytes. And we're gonna think of a way of releasing all of the models, the parameters of the model, and also the data set to the public. And also these models, like I said, the purpose of solving PDs numerically is not just because we cannot solve most of PDs, we cannot solve them analytically. It's because we wanted to support downstream tasks such like inverse problems and design optimization. So we tried these, tried the trained foundation model on a few downstream tasks. They performs reasonably well. Okay, so now let me summarize my talk. So maybe I hope that in the near future, AI can serve as an assistant for mathematicians, not just for pure mathematicians, but also for applied and computational mathematicians, to support in terms of reasoning and also in computations, and not just in activities like research, but also in education. Two of my students, they recently opened a startup that is for AI for educations. Is trying to use current AI models to assist teachers in their teaching activities, or to search students to enhance their learning as well. And I think meanwhile, I think mathematics can be better assisted. Not only mathematics can be assisted by AI, mathematics can better assist in AI development. if we have AI can help us quickly quickly master new mathematical models, quickly to advance mathematical research, mathematics can better assist AI, can provide theoretical guidance of AI models and algorithm design, also can supply high quality mathematical data to train the reasoning abilities of AI, and so that this circle can continue going on and on. This is actually how our team envisioned this interaction between AI and mathematics. So maybe the title for my talk should not be AI for mathematics. It's more of AI and mathematics. But currently, our focus is mostly rely on trying to improve the reasonability of AI and to assist in mathematical research. So with that, I conclude my talk, and I'm very happy to hear any questions or comments from the audience. Thank you.